Unit 7, Periodic Properties, pages 148 to 157, Ionization Energy. All right, let's define it first. Ionization energy measures the energy required to remove the highest energy outermost electron in an atom. So if you have a hydrogen or helium atom, you're looking for the energy it takes to remove one of the 1s electrons. If you had, say, potassium, then the highest energy level is 4s, and you're looking at the energy it takes to remove that 4s electron. So here, for example, is lithium, and when you have lithium with a +1 charge, that means we're going to take one electron from lithium. This is called the first ionization energy, or the I1, is the energy to take the first electron from lithium. Remember, lithium has 3 electrons normally when it's neutral. So when it becomes a +1, now we're left with 2 electrons. Once I have taken the first electron, then I have 2 electrons remaining. What if I take one of those 2 away? Then that is going to be known as the second ionization energy, or the I2. So each electron that you remove is going to be the first ionization energy, followed by the second ionization energy, followed by the third, etc., until you've taken all of the electrons that are in the atom overall. So here is a little diagram, and in the process of ionization, energy is added to move the highest energy electron to the n equal infinity level, where it can separate from the atom, meaning you're removing the electron to an infinite distance away from the nucleus. And so we're going to in infinity. It's going completely away from this atom entirely. So here's the trend of ionization energy on the periodic table. As you go up the family, it's going to take more energy to remove the first electron from each atom. So in other words, it takes less energy to remove an electron from, say, francium in the alkali metal family than it does to take that first electron from lithium. And then as you go from left to right across the periodic table, it's going to require more and more energy to take the first electron from the atoms as you go towards the right on the periodic table. That should make sense, because once you get here, you're looking at the noble gas family. And the noble gases are considered stable because they have a full outer energy level, and so they do not want any electrons removed, and so it's going to require a whole lot of energy to take electrons from the most stable family. Going down a column of the periodic table, electron is further away from the nucleus, so it's easier to remove. Ionization energy drops going down the periodic table. Electrons get closer to the nucleus going across the periodic table to the right. Radius decreases from left to right, and so the atom is harder to ionize, more difficult. Ionization energy increases going across toward the right. Here are some notes about ionization energies. Noble gases have the highest ionization energy, and you can see that here in the graph, where the noble gases have the highest peaks of ionization energy. Alkali metals will have the lowest ionization energy, so that would be lithium, sodium, potassium, all the way across the bottom here. Helium is greater than neon, which is greater than argon, which would imply that because the atomic radius is increasing as you go from here to here to here, it becomes easier to remove the electron, or requires less energy. Neon is greater than fluorine, which is greater than oxygen, which is greater than lithium, because atomic radius increases as you go from neon down to lithium. As you go across a period from right to left, the ionization energy decreases. There are 2 important kinks in the figure above at the points here and here. And at point 1, the electron is being ionized from the boron atom and is removed from a higher energy 2p orbital, and this results in a lower ionization energy for boron. So if we were to actually look at the electron configuration or orbital notation of these two compared to one another, this electron in boron is experiencing much more screening, and it's in a higher energy orbit, and so it's actually going to be easier or take less energy to remove this electron than it would be to take this electron here, which has less screening than 2p, and therefore requires more energy to pull it away from the effective nuclear charge. So beryllium requires more energy than boron because boron's electron is in a higher orbital, which means it experiences more screening. For nitrogen versus oxygen, notice here the nitrogen has a 2p, 1, 2, 3, while oxygen has 1, 2, 3, and then has a pair right there. Well, because of these two electrons sharing the same orbital, they actually are exerting electron-electron repulsions against one another. And so actually, because they're repelling each other, it's going to be easier to take this electron here than it would be to take one of these electrons, which are not experiencing those electron-electron repulsions. So this requires less energy than the nitrogen, and so here oxygen requires less energy than the nitrogen. So pairing the spins raises the energy of the electron due to increased electron-electron repulsions. Less energy is therefore required to remove the electron when ionization occurs. This is the reason why the ionization energy of oxygen is less than the ionization energy of nitrogen. Example 7.42. Which atom, sodium or neon, has the lowest ionization energy and which the highest? So if we compare sodium to neon, neon on the periodic table is in the noble gas family here, as opposed to the sodium, which is in the alkaline earth metal family. And so sodium is in period number 3, so that would be about right here, period 3, whereas neon is at the end of period 2, and so it's right here. So what happens when you move from the end of period 2 to the end of period 3? Well, you get more energy levels, for starters, so your electrons are on the outside energy level, whereas for neon, the electrons are on this energy level here. So because neon here has less shielding, it's going to require more energy to take one of these outer electrons. And because there's more shielding in sodium, it's going to require less energy to remove this outer electron here. And so this is going to have a lower ionization energy, and this is going to have a higher ionization energy, and it's all due to the amount of shielding or screening between the two of them. So another way to think of it is because these are on energy level 2 and these are on energy level 3, that means the sodium atom is much larger than the neon, and therefore the outer electron will be more easily ionized, require less energy to remove. Now let's look at second ionization energies. So here's sodium, and its first ionization energy, I1. After the first electron is removed, it had 11, now it has 10. And then once I remove that first electron, then once I try to go from 10 electrons to 9 electrons, that's the second ionization energy. To understand the trends in second ionization energy, we must remember that the starting point for second ionization is the ion with one electron already removed. For example, to think about how the second ionization energy for sodium compares with neon, you must first consider the electron arrangement for Na+ and Ne+. Example 7.43. Which atom, sodium or neon, has the lowest second ionization energy and which the highest? So the first ionization energy is going to change us from sodium neutral to sodium +1, and so the second ionization energy will go from +1 to N+2. And notice that N+1 is actually isoelectronic to neutral neon. So we're going to kind of think of this in this way. If I compare it to what's happening with neon, neon's first ionization energy is going to bring it to Ne+1, and the second ionization energy is going to be Ne+1 turns to Ne+2. And notice that the neon with a +1 charge makes it isoelectronic with fluorine. So if I actually compare these two to one another, this neon has a higher ionization energy and fluorine has a lower ionization energy, which means the neon +1 will have the lower ionization energy and the sodium plus 1 would have the higher ionization energy. Example 7.44, determine which of these elements has the highest first ionization energy and then which has the highest second ionization energy. So I've made this little rough draft of the periodic table to see their locations, and you'll recall that as we go from right to left, your atoms get larger going this way, which means they're going to have a lower ionization energy as I go this way, and then they get larger going down, and so they'll have a lower ionization energy going down the table. So it's going to go in the order of krypton has the highest, and then it's greater than bromine, which is greater than the selenium, which is greater than the strontium. So strontium here would have the lowest ionization energy of these four. So now if we look at their second ionization energy, remember that the first ionization energy results in a loss of 1 electron for each. And so we'll have krypton plus, bromine plus, selenium plus, and strontium plus. And what these are isoelectronic with are the following. Krypton's isoelectronic with the bromine neutral. Bromine is isoelectronic with the selenium. The selenium is isoelectronic with the arsenic. And the strontium is isoelectronic with the rubidium. And so if we look at where these things are located on the periodic table, here's rubidium, bromine, selenium, arsenic. And so again, as we go from this direction, right to left and top to bottom, we're going to end up with a similar trend where the bromine has a greater ionization energy than selenium, which is greater than the arsenic, which is greater than the rubidium. And so that means that this is the order of the second ionization energy as well. Comparing ionization energies, the diagram below shows why the ionization energy of helium is higher than the ionization energy of hydrogen. All of the energy levels in helium are lower in energy than the corresponding levels in hydrogen. The reason why is simple. As more protons are added to the nucleus, the positive charge of the nucleus increases. As a result, the attractive force between the electrons in the nucleus also increases. The electrons in helium are more tightly held to the nucleus than the electrons in hydrogen. The orbital energies have large negative energies in helium. For lithium, with 3 protons, the orbital energies have are even more negative than in helium as a result of the increased attractive force resulting from the 3 protons in the lithium nucleus. So here, notice it is energy 0, and so we basically just look at this as negative energy going down, and so you would say that hydrogen has less negative energy, helium has more negative energy, and lithium has even more. And this is as a result of adding more protons to the nucleus, which increases the effective nuclear charge. The length of the arrows in the figure above represent the magnitude of the ionization energy. For lithium, the ionization energy is smaller compared to helium. In lithium, the electron being ionized comes from the higher 2s orbital. In helium, the electron being ionized comes from a lower energy 1s orbital. And so this requires more energy to remove one of these electrons than it does to remove one of the electrons from 2s in lithium. Comparing ionization energies for sodium and magnesium. In the diagram below, the length of the arrows is proportional to the ionization energy. For sodium, first ionization removes a 3s electron, this one right here. The second ionization energy would remove an electron from the lower 2p orbital, so it's going to require more energy because it's an electron in a lower orbit. For magnesium, the first 2 electrons are both removed from the 3s orbital. The energy required to remove the third electron here increases dramatically because the third electron comes from the much lower energy 2p orbit. So once you remove this first one out of 3s and we get down to the 2p, it takes a greater magnitude of energy to remove one of these 2p electrons, and then after you take these 2, then there's a big dramatic jump in energy to take one of these 2p electrons from magnesium. The diagram illustrates the general trend that ionization energy always increases dramatically when the electron being removed comes from a filled shell. For magnesium, the third electron is removed from a filled n = 2 shell, and this results in a very high ionization energy. Chemical implications of ionization energy. The magnitude of the ionization energies is responsible for determining the typical charges observed on atomic ions. The plot below shows a comparison of the ionization energies for sodium versus magnesium. Sodium typically exists as a +1 cation because the energy required to convert from Na to Na+ is relatively small. Since sodium plus is isoelectronic with neon, the energy required to make Na+2, the second ionization energy, is way higher. So the +2 and +3 cations are rarely observed. Magnesium typically exists as a +2 cation because the energy required to convert to Mg+1 and Mg+2 is relatively small. Since Mg+2 is isoelectronic with neon, the energy required to turn it into an Mg+3 is much higher, so the +3 and +4 cations are rarely observed. So when you see this big jump in energy, then it indicates that you have an ion that's isoelectronic with a noble gas, and so it takes a lot of energy to remove the electron, which means it's unlikely. So sodium would tend to only be a +1, magnesium would tend to only be a +2, and so on. Here's your note card for this section. So IE stands for ionization energy, and that's the energy required to remove an electron. The first electron removed is going to be called your first ionization energy, or I1. Your second electron removed will be called your I2, or your second ionization energy, and so on and so forth for the rest of the electrons. Here's the general pattern. As you go down the periodic table, remember that your atomic radius increases. The larger the atom, the lower the ionization energy. So your ionization energy decreases because you have so much shielding and you have an electron so far from the nucleus. As you go to the right on the periodic table, the radius decreases. So your ionization energy is going to increase as your atom gets smaller. Electrons further from the nucleus are easier to remove. And if you see a graph that looks like this, then a spike in ionization energy is going to indicate that the atom is isoelectronic with a noble gas. And so it takes a lot of energy in order to take that electron. So that means every electron preceding that point must have been a valence electron. So this graph, for example, would have 3 valence electrons for this atom.